Okay, I'll start it.
Alright, I don't remember actually doing it. So it's just a,
2.5 minutes, yeah.
yeah, we'll give it a bit. That's a nice high time.
Need a warm-up guy. Get the crowd sort of.
Okay, this is a serious talk.
You're booked early, Dan. Okay, well, it's great to see so many people here to help Brad celebrate getting to just about the end of his. He's only got a few minor matters like exams to go after this, but big achievement getting to the end of your honours degree. So perhaps we might find out this morning whether he's learnt anything, at least about spacetimes and their curvature invariants.
Alright, so yeah, firstly I'd like to thank everyone for coming. This is a pretty good turnout, I would imagine. And so yeah, for the past year or so, I have, with John Steele, been studying spacetimes and their curvature invariants. And so for those who don't know, basically this is a study of general relativity, which is our modern theory of gravity. And essentially that studies what are called spacetimes. And spacetimes are just non-Riemannian manifolds. And so in order to study these non-Riemannian manifolds, we'll first need to know a little bit about differential geometry, and that will be the first section of the talk. Oh, focus. Okay, apparently clicked twice. Before moving on to talking about some general relativity, trying to give some actual examples of what we're trying to do. Before then, moving on to talking about invariants, so starting with just some basic examples from areas in mathematics which everyone should have hopefully seen before, and then moving to surfaces, and then finally talking about space-time invariants and then a few applications of these concepts. So as I said, to start, we're going to go over some basic differential geometry. And the first thing we'll need is a basic definition of a manifold. And so a manifold is something that locally looks like Rn at each point. And so basically you want to think about this as something like a surface or a sphere in 2 dimensions. And at each point of M, we have what's called the tangent space, which is the collection of all the tangent vectors at that point P. This is denoted by a TPM. And what's important about this is that TPM forms an n-dimensional vector space. And so just think about this as a surface, a plane to a surface. So when you have a surface, the tangent space is just the plane that's tangent to the surface. And since our tangent space is a vector space, we can define what are called tensors. And so tensors are essentially just, they're multilinear maps, which means they're linear in each of these variables. And so if V is a vector space, and V star is its dual vector space, then an RS tensor is a multilinear map which maps R copies of, well, not R elements from V star and S elements of V to the real numbers. And what will be important are the components of a tensor, because that's generally how we are going to be describing the tensors. And so if Vi is a basis for V, and V with an upper I is a basis for V star, then the components of an RS tensor look like this. And for example, we'll consider a vector. So if X is a vector on the tangent space, then with respect to this basis VA, we can write X is equal to x1 v1 plus x2 v2 up to xn vn. And we usually write this in this compact notation here. So when you see an upper index and a lower index that are the same, it means sum over all the dimensions of the manifold. So in this case, this is exactly that. And instead of describing a vector by x, we will usually refer to we'll call this thing the vector xa, and that's what we'll usually denote by x. Yeah. And so now we're going to discuss metrics on a manifold. So metrics are something that essentially give us a way to measure distance, hence the name metric. And so the metric G on an n-dimensional manifold M is a tensor that assigns an inner product to each tangent space. So you can think about it as essentially it assigns a weighted inner product to every single tangent space. So if you have a standard inner product, say V and W, then you can think of there being, this is too big, but W transpose times some symmetric matrix D times V, where this D is what you would call the metric. And here are some basic examples of the metric. So in flat space, so standard 3D Euclidean space in Cartesian coordinates, a metric is given by this, so just dx squared plus dy squared plus dz squared. I guess it should be important to note that these are your basis vectors, so similarly to how we wrote v before. And you can also write that in spherical coordinates like this. And if you set r to be 1 or constant, then this basically goes away and you're left with the metric of a sphere, which will be important to, I guess, remember for later. Now, one of the main uses for the metric is, as well as giving us a way to measure distance, it also gives us a canonical isomorphism between the vector space and its dual vector space. So essentially what it lets us do is raise and lower indices. So for example, if we start with an upper index vector, say VB, then we can multiply it by the metric, like this, and that'll give us a lower index vector. Yeah. Okay, and so as already previously mentioned, we can think of the metric as a matrix. And so we can rewrite in spherical coordinates the metric like this. And when we think about like a matrix, we can quite easily consider what the inverse metric would be. And so that is, in this notation, this is just the inverse matrix. And in this case, it's given by, denoted with the upper indices, and it's just, the inverse matrix. And so this lets us start with a lower index vector and then raise it. Like that. Yeah. Now, one thing you may notice is that at the point r equals 0, we have divisions by 0, which is obviously not nice. But if we go back to here, we can see that at the origin, this metric behaves perfectly normally, but these are both describing the same space. So at this point where r equals 0, where the metric essentially blows up, we call that a coordinate singularity of the metric, and it is a consequence of the coordinate system that we have defined on our space. Okay, so I think that's enough about metrics for now. And so now we're going to define basically how we describe curvature on a manifold. And these are going to be, I guess, generalizations of like the Gaussian curvature that you have on the surface. We want to find a way to describe the curvature. And so one of the ways we do that is with what's called the Riemann curvature tensor. And so it has 4 indices, and it's basically derived from the derivatives of the metric. Yeah. another curvature tensor we will be considering is what's called the Weyl curvature tensor. And so that is the trace-free part of the Riemann tensor. And so you see you have two A's here, and that means sum. And essentially, if you think of a matrix denoted by two indices, something like this, then the trace of that is just A11 plus A22 plus da 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 da. And that's it in this, summation notation is denoted with an A with one up and one down. And so you see we have this here. So that's why it's called the trace. Two other curvature tensors that will be important to consider is the Ricci tensor, which is just the trace, same way defined before, of the Riemann tensor this time. And lastly, since our Ricci tensor is essentially a matrix, and we can define the Ricci scalar, which is then the trace of the Ricci tensor. And so all of these four quantities will basically form all of our curvature tensors for the rest of this talk. Alright, so now with all that background knowledge, we are ready to move on to talking about general relativity. And so to start, we need to actually know what I mean when I say the word spacetime. And so a spacetime MG is a smooth connected four-dimensional manifold M with a metric of signature -2. And what that signature of -2 means is best explained through example. And so in general relativity, the flat space is not Euclidean space. It's something which is called Minkowski space. And it has a metric which is defined by dt squared and then minus, minus, minus. The t here is your time coordinate, and the x, y, z are your three spatial coordinates. And so if you see here, if you add up the signs, you get 1 minus 1 minus 1 minus 1, which is -2. And so in general, the signature is the sum of the signs of the eigenvalues of the metric. That was a little obvious, but yeah. Okay, and so in the Riemann case, we saw that everything was plus. Yeah, plus, plus, plus. And yeah, in that case, we say that it's Riemannian, but now we don't have that. We have minus, minus, minus. And so because of this, we can have things like vectors having negative length, and more importantly, we have vectors which have no length, effectively, which are called null vectors. And they're all described here. So if Mg is a spacetime and V is a vector, then V is said to be time-like if its inner product with itself is greater than 0, space-like if its inner product with itself is less than 0, and null if its inner product with itself is equal to 0. And so for example, the vector which I'll denote VA, which is given by this, 1, 1, 0, 0, it has length 0 in this Minkowski space metric, which was given here. Okay. Moving on. And so now, since this is a theory of gravity, it is governed by some physical laws. And so the laws basically say that your metric has to satisfy these equations. So here is the Ricci tensor that was defined previously. Here is R, which is the Ricci scalar, which was defined previously, and G is the metric. And this quantity here describes the energy and matter within the region that you're talking about. And if this is 0, then we say that it is a vacuum solution, and they're going to be important solutions to be considering. And what we're trying to get out of these equations is a metric. So when I say solution, I will often mean metric. And I would probably use those interchangeably, you will find. And so our first example of a solution, which is the first non-trivial exact solution found. It is a vacuum solution, so the tensor on the right-hand side of that equation is 0. And it is given by this. It was discovered in late 1915, early 1916 by Carl Schwarzschild, hence the name. And we're now going to try and look at this to extract some information about, about the metric. So the first thing you may notice is that here we actually have the metric of a sphere. And so we can say that this is probably going to be spherically symmetric, and that was actually one of the assumptions that were going into the assumptions that went into led to the solution. And we also see here that at r equals 0, the metric is not invertible, though we could probably say this is due to the fact of the coordinate system, similarly to how we had that problem when we wrote flat space in spherical coordinates earlier. Now, we also have these two other points. Here you see if you put r equals to 2m, you divide by 0. And here if you put r is equal to 0, you divide by 0. And so now we're going to try and investigate the exact nature of these points. So we draw up a quick little diagram. Here is your time coordinate, here is your radial coordinate. And so one thing we may consider is, if I'm sitting far away from this, you probably use the word black hole as well. I also mean this. So if I'm sitting far away from the black hole, and I drop a particle, what will I see as it falls towards it? And so you do your calculations, and you find that it does this red line. So effectively what happens is, as time increases for you, it'll get closer and closer and closer to this line r equals 2m, but it will never actually reach it. So yeah, it asymptotically approaches it. And so you may think, well, why don't we just ignore everything here, since it doesn't really seem to have any relevance for our manifold, since nothing here can actually affect what's happening in here. So you may go, well, what happens to, what will the particle see as it falls into the black hole? And it does this blue line. So it falls straight through and, nothing actually happens. There's no significance of this point. It just, it goes through and then hits r equals 0 in some finite time. And so you'd be inclined to think that this is probably then just a consequence of the coordinate system used, because in fact, this coordinate system, it behaves perfectly nicely. All right. Yeah, but we will still be inclined to say that, so I will use the word event horizon to describe this point, and I'll say singularity when I'm talking about this point. So that's probably enough about some basic general. Let's now move on to just talking about invariance in a very standard setting, and it's going to be similar to the way we construct our invariance in when we're talking about space-time invariance come later. So the first very basic example is under the operation of complex conjugation, the real number doesn't change. It's an invariant of that. And these ones are going to be more important examples. So if we consider an n by n matrix A, then these following quantities are invariant under a coordinate transformation. These are all results from linear algebra, which hopefully everyone has seen. So the eigenvalues of A don't change under a coordinate transformation. The determinant of A does not change. And importantly for what we're going to do is the trace of A doesn't change. And so since our tensors can really be thought of just, big matricey type things, these are going to be quite relevant in the way we define our invariants. Yep. Okay. So now we'll move on to talking about surfaces. Just to give a nice two-dimensional case of stuff we can actually visualize and try to figure out what's going on. So the first, quantity we will define is the Gaussian curvature. And so the Gaussian curvature, K, of a surface, S, is given by the product of what are called the principal curvatures. And so, those who don't know what they are, if you consider a surface here, something like this, is this pen running out? And pick a point on your surface and draw a line normal to the surface. Now, you consider a plane through the normal. It's a much nicer pen. Where this plane intersects the surface, you'll get a line. And as you rotate this plane around, you'll get a whole bunch of lines. And each of those lines are going to have their own curvature. And then what the principal curvatures are, it is the maximum and minimum of the curvatures of these lines. Yeah. And similarly, we also have the mean curvature of a surface, and this one is the sum of the principal curvatures. And you can probably see that these are somewhat related to the invariant quantities we defined earlier. You can imagine that kappa 1 and kappa 2 are probably going to be eigenvalues of some matrix. And so this would be the determinant. And here, this would be the trace, but divided by 2. And it turns out that they actually are. And the operator that they're eigenvalues of is called the shape operator, or the Weingarten map, which I think it is called in classes. And so the reason why we care about these quantities is that we have this theorem from Gauss called the Theorema egregium, and it states that the Gaussian curvature of a surface is invariant under local isometries. So that means that if you have two surfaces that are isometric, then they have the same Gaussian curvature. And so one of, I guess, the big applications of this theorem is that a sphere and a plane have different Gaussian curvatures. So that means you can't project a surface onto a plane without distorting the distances, which is why when you try to get a map of the world on a piece of paper, it always, at the poles, the distances become really, really distorted. And this theorem says basically why that happens. And so now we're going to try and develop similar sort of theorems in the context of spacetimes. Before we can do that, though, we need to actually define our invariants. So invariance constructed through contractions. So this operation here, if A is a tensor, when they have the same index and you get a scalar out, we call that a contraction. So it's constructed through contractions of the Riemann and Weyl tensors and their derivatives. And these are called the scalar polynomial invariants, and they're going to be the center object for the rest of the talk, basically. And here are some basic examples. So you have RABAB, which is the Ricci scalar that we defined earlier. Here you have the Riemann tensor with lower indices and the Riemann tensor with upper indices. Remember that you sum over all of these indices. And you can think of this as being the trace of the Riemann tensor squared, of the square, the trace of the matrix squared. And here you have the Weyl tensor. And when you see a comma with a letter, this means derivative. And similarly, when you differentiate a matrix, when you differentiate a vector, you get a matrix. So you go from 1 indice to 2 indices. If you differentiate a tensor with 4 indices, you get a tensor with 5 indices. And so, okay. So let's now go back to the Schwarzschild metric and try to use these invariants to quickly get an idea of, again, what was happening around those 2 points at r equals 2m and r equals 0. And so let's go back and look at these invariants and see which one of these will be useful in helping us categorize these points. And so let's look at the first one. It's the Ricci scalar. Now it turns out that in every vacuum solution, the Ricci scalar is 0. So that's not going to be very useful in helping us figure out what's actually happening because it's 0 everywhere. Here, this is called the Kretschmann scalar. And if we calculate that in the standard spherical coordinates, we find that it gives us this quantity here. And here we can see, if you put in r equals 2m, nothing happens. It behaves perfectly nicely, but it still does not behave nicely at r equals 0. And so this seems to tell us that, again, the event horizon is just a coordinate singularity. It's not a real curvature singularity. Okay. Now, we might also be interested in, so let's suppose a case where all of our scalar polynomial invariants are 0. What does that tell us about our space-time? And before we move on to actually talking about space-times, we'll just go through what happens with a standard Riemannian manifold. All of our curvature invariants are 0. What does that tell us? And it says here, this theorem says that if MG is a Riemannian manifold, then if all of them vanish, the manifold is flat. And so that's quite nice. And we'll just show a quick little proof of that. So by definition, if the manifold is flat, then the Riemann tensor is 0. So all contractions of the Riemann tensor are just going to give you 0. And similarly, now we're going to go the other way. This one requires a little bit more work. So now suppose that all scalar polynomial invariants vanish. Then in particular, this quantity here is 0. So because the metric is a symmetric real matrix, it has 4, I guess, eigenvectors, or you can always diagonalize it. And we're going to choose a coordinate system that diagonalizes the metric. And so lowering all the indices of the upper R, we get this. And since since mg is Riemannian, all of these quantities are positive because it's diagonal. These are real, so the square of them is positive. And so now we have the sum of a whole bunch of positive numbers are 0. And that means that this quantity here must be 0 because these are non-zero. And so by extension, that says that R is 0. And so now that's quite a nice way for us in the Riemann case. But of course, we're not dealing with Riemannian manifolds. What happens if the manifold is now Lorentzian, or we're dealing with a space-time? And so we will construct an example. So here we have the PP wave spacetimes, which are a family of exact solutions. Basically, they describe propagating waves, so things like gravitational waves, for example. And it has a metric of this form. And it turns out that this metric is not very nice, as it has all, where was I? Sorry. All of its scalar polynomial invariants vanishing, as it says here. And that's annoying. This is not a flat spacetime, so the Riemann tensor is non-zero, yet every scalar polynomial invariant of it is 0. So unfortunately, we can't actually use that to determine whether or not we have flat spacetimes. And you can kind of see why this would be true. Here, in this slide, the proof of this relied heavily on the fact that these were all positive, making this the sum of positive numbers. But in the spacetime case, these aren't necessarily positive, they can be negative. And if they can be negative, then this proof obviously does not work. Cool. And so now we're going to call a spacetime that has this property where all of its scalar polynomial invariants vanishing, call it a vanishing scalar invariant spacetime, or VSI for short. And we're going to have this question: can we actually classify in some way every spacetime that has this property? Is there a way we can go, okay, if it has this property, then it satisfies these other criteria? Draw it in, compact into some nice little group. And it turns out we can. And so we'll actually define what this is, because it's a bit beyond this talk. But a spacetime MG has all, if this is true, then it is of this class. So you can effectively say, think we have, we have some set of spacetimes, and somewhere in there we have all the VSI spacetimes. And it turns out that we can all group them in some other well-known category that's already well studied, called the Kunz spacetimes. Which is very sideways. Yeah. And so that's quite nice. And so you may ask, well, if we remove, well, since the flat space and PP waves can't actually be determined or distinguished with the scalar polynomial invariants, if we ignore everything of this form, can we determine uniquely a spacetime by its scalar polynomial invariants? And it turns out that if you remove everything from the Kunz class, it turns out you actually can. And so this is a big theorem that says that basically, if a spacetime is not of the Kunz class, then it can be classified by its scalar polynomial invariants. And that is a very, very nice theorem. Yeah. Okay. But what can we do about these spacetimes that are of the Kunz class? Is there any way we can we construct other things that work for that? And it turns out that you can. And so here we have what is called the Cartan invariants. And so if you have RQ being the set of the Riemann tensor and its derivatives up to the qth order, then contracting that with a basis gives you the Cartan invariants. And for example, if A, B, C, D is a basis, then an example of a current Cartan invariant is this. So I'll do a little example on the board over here. It should be noted that the A, B, C, Ds don't actually need to be distinct. So if you consider, rather than the Riemann tensor, let's just consider a matrix, A, B, which will have some eigenvalue called V, A. And then if we contract it, and so since this is an eigenvector, this is going to be equal to, say, lambda times VA for some eigenvalue lambda. And then if we then contract that again, this should be lower. And then if we contract that again with the vector, we get lambda VB, VB, which is equal to, like, say, lambda times the norm of V squared. And we can always pick the eigenvalues in a way that, you know, the norm of the eigenvectors are 1. And so this is effectively just lambda. And so, so I guess you could think of these as categorizing your tensors by things like the eigenvalues, whereas before we were categorizing them with things, you know, like the trace. And so I guess that's the distinction here. But of course, this one relies on you having an invariant way to classify your basis elements, because you need to be able to write these in different coordinate systems and make sure that they are actually the same, the same basis elements. Okay. And so in this case, we have this theorem. And so it says that basically if M and M bar are two different spacetimes, then there exists a local isometry between them, if and only if that basically they have the same Cartan invariants, which is quite nice. It gives us a way to actually deal with these, I guess, problematic spacetimes. So yeah, okay, so that's enough, I guess, theory behind it. We're now going to try and find some applications of these things. And so one of them is locating the event horizon. Because whilst, you know, earlier we were trying to find out if the event horizon was a real singularity, we might be interested, you know, at what point would the particle actually pass through it? Because for that, you know, for the particle, there is no event horizon. But we might be interested in, you know, exactly where that lies in that coordinate system. And so essentially what we're going to try and do is construct scalar polynomial invariants that say vanish only at the event horizon. And since they vanish at the event horizon, it doesn't matter which coordinate system you write it in. If it's 0, that's the event horizon. And if we construct this quantity for the Schwarzschild spacetime, we'll see that it vanishes at and only at the event horizon. And it's also strictly negative outside the horizon and strictly positive inside the horizon. So that's quite nice. And if we compute it in the standard spherical coordinates, we get that it's this quantity. And as you can clearly see, put r equals 2m, you're 0. R greater than 2m, it's negative. And r less than 2m, it's positive. And so this is quite a nice, I guess, quantity, because this could be calculated in any coordinate system. And we'll always be able to say, you know, are you outside the event horizon, are you inside the event horizon, or are you at the event horizon? But of course, the Schwarzschild spacetime is not the only solution. Realistically, so the Schwarzschild solution describes something that's not rotating, and realistically, like, bodies rotate. And so you may ask, you know, well, can we actually do this for a more general spacetime? You know, you could take a rotating body, we will be able to find its event horizons in a similar sort of construction. And so I'm not going to actually compute them because rotating solution is actually a lot more complicated, but you can. And this exact quantity will find interesting points on that spacetime, the rotating spacetime, which is called a Kerr solution. But in order to locate the event horizons, you'll actually need to use a bit more complicated scalar polynomial invariants. Okay. Yeah. So one last use, we're going to try and, since, as we saw, all of these spacetimes are very, very coordinate dependent. And we're going to now try and find a way to get a general picture of what is happening in the spacetime that is coordinate independent. You know, that won't give us a distinction between, you know, one case, you know, the particle went up to, you know, asymptotically approach the event horizon, and in the other one, it passed straight through it. So we want to find a way to get a nice invariant picture of what is actually happening in these spacetimes. And so, first we're just going to do an example of a surface. So this surface here is called an elliptic paraboloid. So here you have an ellipse, and this is a parabola. And so what we're going to try and do is plot the gradient of, in this case, the Gaussian curvature in order to get away, to find a way, I guess a coordinate-independent way of describing how the curvature behaves on the surface. So yeah, as I said, basically what you have is one cross-section, here you have height, and this is what you see, and the other one you have an ellipse that moves around with theta. Here I'm only plotting from theta equals 0 to pi, so this is realistically just half of it, but it doesn't matter, it's symmetric, so you know. And so what this says is that at theta equals 0, pi on 2, and also pi, the curvature is only changing as you move up. It doesn't change as you move around. And you can kind of see that when you look at this picture, because as you move up, the curvature is always changing as you move up and down. Whereas if you move along here, as you go along here, it decreases, hits a point, and then starts increasing again. Hits a point, starts decreasing as you move along. And so at these points where it changes, there's obviously no change in the curvature. And so that's why you see these points where it's just nothing happening. All right. And so now we're going to try and do a similar sort of construction with the spacetimes that we've already introduced, namely the rotating solution and the Schwarzschild solution. And firstly, we need to actually define what invariants we're going to look at, because we have a lot more to look at than just the Gaussian curvature that we had for a surface. And so here are the invariants that we use. We use the Weil tensor and lower and upper. And the star just means this quantity. This epsilon AB EF is the Levi-Civita tensor, and it's 1 if AB EF is an even permutation, and -1 if AB EF is an odd permutation, and 0 if you have repeated indices. And so from these, complex invariants, because it's I, that I is just the standard imaginary unit, we construct 4 real invariants, which is given by the real part of this, which is just this and this, because these contractions are all real, and the imaginary parts is just, that and that. And so from that, we construct our 4 invariants that we're going to be looking at for the next section. If we calculate these in Schwarzschild, for the Schwarzschild metric in your standard spherical coordinates, we see that we have this relation, and the invariants are also just purely real, so we only have 2 to look at, and they both are essentially the same thing, so we're only going to be looking at just the 1 in this case. And so when we do this for the Schwarzschild solution, we get this picture here. And so what this picture essentially tells us is that, so this is a plot of the gradient of those invariants which I just defined. And so it says that no matter which way, here x and z are your standard Cartesian coordinates, and it says that no matter which way you move away from the metric, the curvature is always, in this case the arrows point to where it decreases, but it doesn't really matter. I mean, it's always decreasing as you move away from the center. There's nothing else happening here. It gives us this picture, it's of a spherically symmetric body, which is what we would expect. I mean, the Schwarzschild metric describes a body that is just sitting there, it's not rotating, it doesn't have charge, it's just a mass m, and this nice spherically symmetric solution is what we would somewhat expect in that sense. So now we're going to move on to what's called the rotating solution, which is the curve. So as I mentioned before, it is also a vacuum solution, and it describes a rotating mass. So now we have our mass in the middle, except we can see what happens when it rotates. And this time we're going to have all 4 of our invariants non-zero, and but they are still related by this quantity here. I'm not actually going to write down what they are because it is a lot more of an ugly expression than the Schwarzschild case, but I will give you a picture of what it looks like. So this is what happens when you introduce rotation, and you can suddenly see that the curvature is a lot more complicated. There is a lot more happening in the Kerr solution. So you see you have, before everything was moving away, but here we have critical points here, here, and here. We have points where it all flips back around on itself. And so what you may notice is that excluding the 0, 0 coordinate, all the critical points occur along the z-axis for both, except at this point x equals 1. So you may wonder what's happening at x equals 1. Well, it turns out that these aren't quite Cartesian coordinates. The Kerr solution is a lot more complicated. And so because of that, it doesn't have a singularity at the origin. It has what's called a ring singularity, which is at the coordinate point r equals 0 and theta is equal to pi on 2. And so in this coordinate system, this point x equals 1 actually corresponds to the coordinate singularity, the curvature singularity of the black hole. And this line between 0 and 1 is actually all just r equals 0, which is kind of, I guess, interesting. And we also see, that this has 1, 2, 3 critical points along the z-axis, and again we have 1, 2, 3. And since this has got quite a complicated structure compared to the Schwarzschild case, we're actually going to be interested in what happens with the other invariants. Even though they're still related by that relationship, it might tell us some more if we look at the other relations. Oh, I should also mention that this solution, it's not spherically symmetric, as you can probably see, but it is actually symmetric. So, down here we have this flipped over, along here we have this flipped over again. So it's actually symmetric, but it's not spherically symmetric. And now, we bring up the other two, we can see they actually have quite a similar structure as we would expect. Again, everything seems to be pointing towards this point at x equals 1, z equals 0. But this time we now have, instead of 3 points along the z-axis, we actually have 4. So 1, 2, 3, and 4, and similarly here, 1, 2, 3, 4. So yeah, that's that. And what's also, I guess, interesting about these is that, so with a rotating black hole, you still have event horizons. And depending on how fast the black hole is spinning, these points can actually lie outside of the event horizon. And you could actually use that to extract information, depending on how many of these, so say you're running some numerical simulation, depending on how many of these are lying outside of the event horizons, you can actually extract information about how, the mass of the black hole and how fast it's rotating and all these nice properties of it, which is good. And yeah, I think that's about it. So this is just a picture of all 4 quadrants for the I1, and I don't know, I think it's a nice picture. So yeah, I put it up there. Yeah, thank you everyone. I think that concludes my talk.
Any questions or comments from Brad?
Yeah.
So if I understand correctly, are you saying that because of that theorem says that all non-VSI spacetimes can be characterized by the invariance, basically mean that all Kundt spacetimes are VSI?
No. So the VSI are, as I guess, they don't really form a set, but they're a subset of the Kundt spacetimes. Yeah. So it's not everything, but it turns out it's like if you get rid of everything that's vanishing and a little bit more, then everything works nicely.
So what's the extra bit that is Kundt spacetime but it's not VSI?
There's definitions of it in my thesis, but it all comes from stuff which I didn't introduce in the talk because it's a bit more complicated. And yeah, I guess if you want, you could probably Google it or read my thesis or whatever. But yeah.
Just wondering about the history of that. Actually, when's that sort of
Yes.
result about the fact you can characterise the
That
non-Kundt
paper
ones?
came out in 2009.
So it's pretty recent then.
Yeah. This is all quite recent. I mean, it's like I read a paper from the late 90s, early 2000s, which was like, so because a black hole can have parameters of mass, spin, and it can also have charge. And I read a paper which was like, yeah, this is the first time I'm calculating this quantity. It took, half an hour on this computer that I had. And so a lot of these things realistically have only been achievable in the past 15, 20 years or so. So, yeah. Yep.
I'm a little confused about part-time invariants.
There are. I think the example that I have is using spinners. You can define in what's called the principal null directions of the spinner corresponding to the Weil tensor, and that will give you a invariant way to classify, I guess, your directions. Similar to how your eigenvectors of a matrix, I guess, give you an invariant way to classify. Like, you can always calculate them and they'll always point in the same direction. So it's a similar sort of construction. Does that make sense?
So that you can't always get a basis of principal null directions.
I think you can.
Yeah, Jonathan's right. There are cases where you don't get a basis of principal null directions. But you
But
can
you
get,
do.
well, I mean, you can always get a basis of principal spinners because there's only two of them.
Yeah.
You just have to pick one. Well, one of them is given and one of them is sort of
A bit.
more or less.
I mean, you always have, I mean, okay, it won't necessarily form a basis, I guess, but you always get some amount of them. And if these don't have to be distinct, right?
I mean, it's similar in a way to that you don't always get a basis of eigenvectors.
Yeah.
But you can get a basis of generalized eigenvector.
Yeah. And so, I mean, you know, if you only have two here, then you can do this construction with just, I mean, here you could just have A. You don't have to have all four of them. I don't know if I explicitly stated that, but I mean, that was what, okay, I rubbed it off, but that was what I was doing with the eigenvectors, where I used the same eigenvector twice. Does that make sense?
But I mean, you can build it. If you don't have enough out of the tensor itself, you can differentiate, and that might give you more.
Yeah.
In these BSI cases, they don't give you more, and that's part of the problem.
Any other questions?
Yeah.
So you said the rotating case is a lot harder. Where does the rotation come into the equation?
In
field equations.
So, I guess it kind of, well, in the actual equation itself, it's still a vacuum solution. So it's still saying essentially, essentially the field equations say, if you think of the Riemann tensor being a matrix, and rather than having four indices, and you consider the vacuum case, then all it says is the trace of the matrix is 0. And everything that has trace of the matrix 0 satisfies those equations. So it doesn't, I guess, it's just another solution that satisfies that the trace of the matrix is 0. And it just turns out that the parameter that you write, A, corresponds to the spin, or the angular momentum of the black hole. I could bring up the actual solution, but it's quite a bit more ugly. Yeah?
So you mentioned it's also like the charge case, and the charge case. So is that like the non-vacuum solution?
Yeah, that's a non-vacuum solution. So you have some energy tensor on the side that, yeah, again changes that. It's actually quite a bit more similar to the rotating case. Like, there was obviously a big difference between Schwarzschild's rotation, but the difference isn't so great when you add charge.
48 years is the difference. Put it that way.
Yeah, so the curve metric was discovered in like 1960s, whereas the Schwarzschild was 1915. So it was a good 50 years or so before they actually were able to, I guess, generalize their solution. Anything else?
Okay, well, I think we can just thank Brad for a very nice talk.